Chapter 10, Liquids and Solids. Our outline is intermolecular forces, liquids, changes of state, solids, metallic solids, ionic solids, network atomic solids, also just called network solids, molecular solids, and finally phase diagrams. Intermolecular forces, IMFs, we often call them IMFs. So we will get into those by looking at how liquids form. What we have to do is remember gas, liquid, solid, the three common phases of matter. In the gas phase, the molecules are very far apart. In the liquid and solid phases, which we call the condensed phases, the particles are very close together. They're constantly encountering each other. Alrighty, so how liquids form. Consider liquid or gaseous nitrogen at room temperature, 25 degrees Celsius, and typical pressure, 1 atmosphere pressure. So basically room temp and pressure. It's an ideal gas. There's no attraction between particles. So that's our ideal gas premise. No attraction between particles. They hit each other, but they just bounce away from each other. So now we decrease the temperature. Eventually, as we go to lower temperatures, a real gas forms. Still a gas, but now there are attractions between particles. But the particles are still in the gas phase. We decrease the temperature more. Of course, decreasing temperature means the kinetic energy, Ke, is decreasing as well. Eventually, the attractions between the particles dominate over their motion, their ability to get away from each other due to their kinetic energy, and the liquid forms. For nitrogen, that occurs at negative 196 degrees Celsius or 77 Kelvin. Very cold. The attractions that cause it to go from the gas phase to the liquid phase are called intermolecular forces, the IMFs. Alrighty, a quick review of bonds, attractions. When we have ions, we have the ionic bond, and that's between ions. Getting a sense of the range of the attraction, the ionic bond attraction, it roughly varies from about 500 to 5,000 kilojoules per mole. We talked also about the covalent bond. That would be the bond between atoms. Typically, it is in the range of 100 to 1,000 kilojoules per mole. This new kind of attraction, this intermolecular force, this IMF, this is not between ions, not between atoms, but between molecules. And its strength is often in the range a little bit over 0 to at most 100 kilojoules per mole. So notice that by contrast, IMFs, that kind of a force, is much weaker than the ionic or covalent attraction. IMFs are due to the attraction between the partial positive end of one molecule or particle and the partial negative end of a nearby particle. They're like a very weak ionic sort of bond, ionic attraction. So here are diagrams of that. So let's say we have a molecule, a diatomic molecule, A, B. So it's composed of some atom A, some atom B. Let's say that the atom A has the partial positive charge on it, atom B the partial negative. Well, we would have a bunch of those molecules, those AB molecules together in the liquid phase, and they all would have the partial positive end at A, the partial negative end at B in our diagram here. Notice that opposite charges attract, the partial negative attracts the partial positive. That is the IMF that we're talking about. Often IMFs are shown as dotted lines. So in the middle diagram with the color, we see the red showing the partial, the more partially minus end of the molecule, the blue, the more partially positive end, and of course the opposites attract. So we see a bunch of these attractions given by the red dashed lines. Well, there are also repulsions, and those would be between like charges. So the molecules arrange themselves together to maximize the attractions and minimize the repulsions. The last diagram is with water. So we know that in water, which is polar, we have oxygen with its partial negative charge, the hydrogen partial positive. So what that means is an H is attracted to an O, and we have those IMFs in water. IMFs exist between molecules, so they're between a molecule, whereas a covalent bond, that's between atoms within a molecule. In general, IMFs are weak with strengths 1 to 10% of the strength of a covalent bond. But without IMFs, many liquids and solids would not exist because there would be no attraction between the particles and they would be in the gas phase. So IMFs exist, although they are weak. So IMFs are weak, and that is why when liquid water evaporates to gaseous water, we still have water. We have not broken the stronger covalent bonds within water. The three IMFs types that we will talk about are the dipole-dipole force, often symbolized Dd, the hydrogen bond, often symbolized H, and the London dispersion force, often symbolized Ld. All right, so first, the dipole-dipole force. For this one, the molecule must be polar, and being polar, the molecule contains a permanent separation of charge, a permanent dipole. So the electronic dipole is the separation of charge. If it's permanent, it means the molecule always has that. And a polar molecule always has that permanent separation of charge. So to be an IMF type that's dipole-dipole, the molecule must be polar. So what we have there is the positive end of one molecule is attracted to the negative end of another. And we see in our diagram the example given of the molecule HCl. So Cl is more electronegative. It's got the partial negative charge, H partial positive charge. And so each HCl is surrounded by many other HCl molecules in the liquid phase or the solid phase, where the Cl end is getting close to the H ends. And those attractions are the dipole-dipole IMF. In this table, what we have is HCl liquid vaporizing to HCl gas. Delta H of vaporization is the energy that must be supplied to cause that liquid to gas transition. And it's 18 kilojoules per mole for HCl. It is the energy needed to overcome the dipole-dipole forces within the HCl liquid. So 18 kilojoules per mole. By contrast, if we take HCl and we want to break the bond between the hydrogen and the chlorine, break that covalent bond to give H atoms and Cl atoms, then we have to supply a much larger amount of energy. For HCl, that is 427 kilojoules per mole. So that would be the bond energy of that HCl bond. And the 18 is much less than this 427. In fact, 18 in comparison to 427, that's only 5%, as our calculation there shows. What I'm trying to emphasize here is the IMF forces are definitely weaker than the covalent ones holding the whole molecule together. The IMFs are what keep it in the liquid phase, in the solid phase. They are what must be overcome to cause the liquid to be evaporated. Okay, so that's the dipole-dipole force. The hydrogen bond, so the next kind of IMF that we'll talk about. It is the attraction between a partially negative oxygen, nitrogen, or fluorine and a partially positive hydrogen bonded to another O, N, or F. So the criteria for the hydrogen bond is the molecule must be polar, kind of like the dipole-dipole situation, and the molecule must contain H bonded to N, O, or F. Remember that F is the most electronegative element on the periodic table, O is next in line, and N is a little bit less electronegative, but still very electronegative. And also, F, O, and N are very small, as is hydrogen very small. So what happens is when there is H bonded to either N, O, or F, we end up with a very strongly partial positive end on the H and partial negative end on either the N, O, or F, whichever is present. And those atoms are all very small, so they can get close together. They're more highly charged. What we end up with is a very strong partial positive, very strong partial negative. That attraction we call the hydrogen bond. And in this table here, we're seeing that in HF. So there we have H bonded to F. So we have the hydrogen bond. We have the partial positive H, partial negative F. So the F is attracted to the H of other molecules nearby. We also have the hydrogen bond present in water because we have H bonded to O. That's our middle diagram. In the third diagram, we have water in formaldehyde, which is this C double bond O molecule with two H's on the C. So indeed, in the CO, the CH2O, the lower molecule in that picture, we don't have H bonded to O. But in water, we do have H bonded to O. So the H of water is attracted with the hydrogen bond to the O of the lower molecule. That is to say, IMFs can be between different molecules. Formaldehyde and water are soluble together. The H bond is approximately 10% as strong as the typical covalent or ionic bond and is typically stronger than the dipole-dipole force. So the boiling point, BP, is the temperature at which a liquid boils. A big boiling point, that implies big IMFs within the liquid. So here we have a graph of boiling point versus the period. We have the data shown with colors. So the purple is group 4A on the periodic table. So that would be the group involving carbon, silicon. The green data is for group 5A. So that would be the group involving nitrogen, phosphorus. And then we have the orange data, that is for the group involving oxygen, sulfur. And lastly, we have the red data, that is for the halogens. Notice that in all cases, whatever other element is involved in the molecule is H. So that you could say is kind of equivalent. So we're kind of like looking at the different atoms involved, different periods, different kinds of bonding. So going to the purple data, CH4, SiH4, GeH4, those are all nonpolar. So those would have not dipole-dipole or hydrogen bonding capability. We'll come to what they have a little bit later. Bear in mind that their boiling points are low. Low boiling points mean not very strong IMFs. Going to the green data, we have the nitrogen group, and notice that NH3 has a very high boiling point in comparison to the other data that's associated with the green line, the PH3, the ASH3, and the SBH3. That's because PH3, ASH3, SBH3, those are all polar, so they would have the dipole-dipole IMF, not the more strong hydrogen bonding. In NH3, we have N, we have H, we have what it takes for the hydrogen bond. The hydrogen bond is stronger than the dipole-dipole, so the boiling point of ammonia is higher than that of the others. And then we go to the oxygen, the orange data. We see water way up at the top, higher than H2S, H2SE, H2TE. And those are all polar molecules, but the H2S, the H2SE, the H2TE, those can only do dipole-dipole type force. But the hydrogen can do the hydrogen bonding, so it's much higher. Lastly, we have the halogens, and we have HF at the top of the list. So that's because, again, it can do hydrogen bonding, whereas the other ones can only do dipole-dipole. So what we have over on that column beside the graph, we have the boiling point of HCl is negative 85 degrees Celsius, very low, whereas the boiling point of HF is 19.5 degrees Celsius. So it's almost a liquid at room temperature. It has, on a very cold day, it would be a liquid due to its strong interactions between those HF molecules. The hydrogen bond in the HF versus the dipole-dipole force in the HCl. Alrighty, so going on, we have our third IMF, which is called the London Dispersion Force, LD. This last IMF is present in all molecules and atoms. It is an underlying IMF in polar molecules and the only IMF in nonpolar molecules and atoms. So if we have a nonpolar situation, then we have only the London dispersion force present. So in atoms and molecules, the electron cloud is not frozen. The electrons can jump around, they can spend more time at one end of the molecule or atom than at the other. The London dispersion interaction happens when, let's say we have molecule 1. The electrons in molecule 1 move to one end of the molecule, creating an instantaneous dipole. So notice that molecule 1 is nonpolar, and its electrons normally would be rather equally distributed, but they slosh about, and for some reason they're spending more time on the right end of the molecule than the left. That gives the right end a partial negative charge. Now, it's instantaneous. It exists for a moment, then it goes away. This instantaneous dipole induces electrons in molecule 2, so a nearby molecule, to move to the other end, creating an induced dipole. Both dipoles are temporary, so they just exist momentarily. Molecule 2 and molecule 1 experience an attractive force called the London dispersion force. This is the only IMF that exists in nonpolar molecules. So in our diagram on the left, we have atoms. Now, atoms can be condensed into the liquid phase, like take argon atoms. But normally an atom has pretty evenly distributed electrons. In our diagram here, for atom A, atom B at the top with no polarization, the electrons are distributed evenly. But then they move about and they move over to the left side. That gives the left side of the atom a partial negative charge, right side a partial positive charge. And it induces, so go to that bottom diagram on the left, it induces the electrons to be pulled toward the left in that atom A, in the atom B, that nearby atom. And the attraction between now atom A and B is this London dispersion force. This can also happen in molecules, so take H2, it's nonpolar. The electrons move to one side, the left side, in the molecule A, and that induces a similar situation to occur in the nearby molecule B, and then they're attracted momentarily by the London dispersion force. In general, the London dispersion force is weaker than the dipole-dipole force, but it increases with increasing molar mass, since atoms or molecules with many electrons can more easily develop an instantaneous dipole and induce dipoles in neighboring atoms and molecules. Here are the boiling points of different carbon-hydrogen compounds. So we have methane. That's the main component of natural gas. That is CH4. So we have just one carbon molecule, of course, 4 hydrogens. Its boiling point is negative 164 degrees Celsius. Ethane, which is now 2 carbons big, a little bit bigger, a little higher molar mass than methane, its boiling point is a bit higher, a little less negative. We go to propane. We have 3 carbons, of course, 8 hydrogens. So we're getting higher molar masses, we're getting just bigger molecules, more electrons. The electrons can more easily slosh about and create the London dispersion interactions between them. The boiling point has gone up more. Butane, it's just a little bit below 0 degrees Celsius. Pentane, so now we have 5 carbons, so much bigger. Its boiling point is a little bit above room temperature. So pentane would be a liquid at room temperature, whereas the ones smaller are all gases at room temperature. We get to hexane, 1 more carbon, and even higher boiling point. Because remember, boiling points can be a measure of the strengths of the IMFs. All of those molecules, methane, ethane, propane, butane, pentane, and hexane, those are all nonpolar. Okay, here's a problem. Example, which halogen molecule, F2, Cl2, Br2, or I2, exhibits the greatest IMF and which has the greatest boiling point? And given the boiling points, which are gases at room temperature? So they're all nonpolar, that's a hint. So think about what we talked about with molar mass to answer that problem. So go back later and do that one, or stop the video and do that and come back. So a summary, dipole-dipole forces, and the example is given here in formaldehyde. We have the partial negative O, we have the partial positive carbon end, and you see how the molecules attract each other, opposite charges. That's the dipole-dipole in that polar molecule. Hydrogen bonding, HF, we had talked about that one before. So that's like the dipole-dipole force, except it's even stronger due to the small size of those atoms involved and the big electronegativity differences between H and the either O, N, or F. And we call it the H bond because it's a strong one of the three IMFs. And then here we have helium as the example of the London dispersion force. Okay, so now we have some examples. Identify the most important IMF present in solids, or you could say liquids, of these substances. So what you have to do is draw the Lewis structure, decide about the shape, decide about the polarity. Also, if they're polar, do we have H bonded to O, N, or F? If they're nonpolar, then of course we only have London dispersion. So come back and do that one later. So now we'll talk about liquids, and a lot of these properties of the liquids that we will talk about are due to the IMFs present. And from those properties we can get a sense of strengths of IMFs. Okay, delta H of vaporization. It is the energy that must be supplied to vaporize a liquid, to overcome the liquid's IMFs. It increases with increasing IMF strength. In water, to go from liquid water to gaseous water, we have to supply that energy. Delta H of vaporization of water is 40.7 kilojoules per mole. In general, when we go from liquid to gas, we're having to supply energy. It's an endothermic process. That would be the delta H of vaporization. On the other hand, to go from the gas back to the liquid, energy is given off, and it would be delta H is negative. It's an exothermic process to go in the reverse direction. Boiling. Liquids evaporate. Liquid forming the gas is what occurs during evaporation. The weaker the IMFs, the more easily a liquid will evaporate and become a gas. So we have the diagram there where that box with the molecules shown as circles in it, that's meant to be a beaker, and we have a liquid in there, and between the molecules we have IMF forces holding them together close enough that we're in the liquid phase. When they evaporate, they go to the gas phase where there are no IMF forces present between molecules. The more that evaporates, the more gas there is above the liquid. The amount of gas present above the liquid is its vapor pressure. The weaker a liquid's IMFs, the greater its vapor pressure. When the atmospheric pressure, that is pushing down on the vapor, equals the vapor pressure, the compound is what we call boiling, and we would see bubbles rising from the bottom. The boiling point is the temperature at which the compound boils. So to evaporate and then finally boil, the liquid must overcome the IMFs. The higher the boiling point, the greater the IMFs, as we have been talking about, as we, in examples above, talked about boiling points. Liquids that readily evaporate are called volatile liquids, and those that don't readily evaporate are non-volatile. So in this table, what we have is, over on the left, a diagram. Again, it's a beaker with a liquid in it, and the liquid is vaporizing, and there's a vapor pressure above the liquid. When the vapor pressure equals the atmospheric pressure pushing down on it, so imagine we have the arrows pointing down representing the pressure of the atmosphere pushing down, and we have the vapor pushing up on the atmosphere. When those two are equal, the liquid is boiling. We see bubbles rising from the bottom. If the atmospheric pressure above the liquid is lowered, then the liquid more readily boils. It boils at a lower temperature. The atmospheric pressure decreases with increasing elevation. So as you climb a mountain, the atmospheric pressure is decreasing. You might feel it in the lower amount of oxygen present. So you might feel you need to breathe more quickly and deeper. So the boiling point decreases with increasing elevation. Here are boiling points of water at various elevations. So going to the table on the right, we have at sea level, so elevation 0, the atmospheric pressure typically is 760 torr. Boiling point is regular boiling point of water. We call it the normal boiling point of water, 100 degrees Celsius. If we climb up to the top of Mount Lassen, where it's about 10,000 feet elevation, the atmospheric pressure is about 710 torr. Water would boil there at 90 degrees. And it won't get hotter. It will boil at 90 degrees. So we might have to cook our pasta if we were that ambitious to be cooking pasta up on the top of Mount Lassen for longer. If we were to climb up to the top of Mount McKinley in Alaska, which has a 20,000 foot elevation height, there the atmospheric pressure is only 340 torr, and water would boil at about 80 degrees Celsius. Again, we'd have to boil our pasta for a lot longer. Wow, if we were very ambitious, we climbed to the top of Mount Everest, 30,000 feet. Mind you, we'd have to have supplemental oxygen and so on. We would never be cooking pasta up there. But if we did, the water would only be at 70 degrees Celsius, and it would remain at that temperature the whole time we were boiling it. It wouldn't get hotter because the atmospheric pressure is only 240 torr typically. All right, liquids, they have surface tension. And that is the tendency of a liquid to minimize its surface area. This causes liquids to have a skin on their surface that resists penetration. It's harder to kind of like poke through. The stronger the IMFs in the liquid, the greater the liquid's surface tension. So high, big IMF, we expect big surface tension. Or we could say if we measure the surface tension of a liquid to be high, we would deduce that the IMFs in the liquid must be high. And we have the diagram on the right and words with it. Molecules at the surface of a liquid interact with fewer molecules than those in the interior. So look at the molecule on the surface. We see it shown interacting with 4 other molecules. Whereas take the molecule in the middle, we see it's interacting with 6 other molecules. And this imbalance of the molecules at the surface versus those in the interior make it so the molecules don't want to be at the surface. They'd rather be where they're more in the middle, where they're more balanced. So the liquid reacts by minimizing its surface area and making for a surface tension. Water has a pretty high surface tension due to the hydrogen bonding capability in water. And if we carefully set it up, we can float a paperclip on water. Now realize that paperclips, at least this metal one is, well, it's made of a metal, and metals are denser than water. So higher density means it should sink. But if we very carefully place the paperclip on the surface of the water, like using a pair of tweezers, we can actually get it to just float there due to the high surface tension of water. Okay, so far of our liquids, we've talked about they have vapor pressure, that's a measure of IMF strength. They have boiling point, that's a measure. We have surface tension, that can be used as a measure. And next we'll talk about viscosity, which can also be used as a measure of IMF strength. It is a measure, viscosity that is a measure of a liquid's resistance to flow. Highly viscous liquids have large IMFs. To be highly viscous means to resist flowing. Maple syrup, much more viscous than water. It's got stronger IMFs than water. Glycerol, whose shape I show there, the structure, has a lot of OH bonds. Glycerol is also thick. It has a high viscosity. It's kind of like maple syrup, but maybe even a little more viscous. It's a polar molecule. In fact, it can do hydrogen bonding with other glycerol molecules. A hydrocarbon like gasoline is made of just carbon and hydrogen. Those all are nonpolar, and that means we only have the LD interactions. And hydrocarbons typically have very low viscosity. If you've ever put gasoline in a container to bring, let's say, home to put in some, like a lawnmower, you maybe have noticed how the viscosity of it is very low. It's very easy to spill. So as IMFs increase, viscosity increases. So there's an example problem for you to look at. Come back and do that later. Capillary action. That's another property of liquids. It is the rising of a liquid against gravity into a tube or up a paper towel, for example. And this capillary action gives rise to the shapes of meniscuses. In the left diagram, we have water in a glass, like a burette. And look at the lower diagram, we see that the water has a concave meniscus. The water kind of creeps up the sides of the glass. And we see in that expanded circle diagram the water shown versus the glass, which is shown with those yellow molecules. The water likes the glass. Glass is very polar. Water is polar. Water likes to climb up it a bit, and that's why we get that shape. By contrast, when we have mercury in glass, it has a convex kind of surface. The mercury does not like the glass. The mercury molecules like each other, not the glass. And that's what that expanded diagram is meant to show us. They would rather stay together than be climbing up the glass walls. So that describes different meniscus shapes. Vapor pressure, another property of liquids. Vapor pressure is the pressure of the liquid over let me go back. It is the pressure of the vapor over the liquid at equilibrium in a closed container. We talked about vapor pressure earlier, but this is now, it's kind of like more technical definition. So we have to have the closed container. We have to have it so it has sat for a while, that is to say at equilibrium. And then the pressure of the vapor, of the gas in there, would be its vapor pressure. So in our beaker A, initially net evaporation occurs. So we put a liquid in there, we seal it, and the molecules are just evaporating because there weren't any gas ones in there to start with. The amount of liquid will decrease a little bit. In B, as the number of vapor molecules increases, the rate of return to the liquid, that's condensation, increases until the rate of condensation equals the rate of evaporation. So notice that we have arrows pointing up and down. And when they're equal, the system's in equilibrium. No net change occurs in the amount of vapor or liquid. It is in equilibrium. In that diagram, we have rate of either evaporation or condensation versus time. Initially, we only have the blue line, we only have the liquid, so we only have evaporation occurring. But as we get molecules in the gas phase, we start getting condensation to occur. And the amount of condensation increases as we get more gas molecules, to the point where the rate of evaporation equals the rate of condensation, and that is where equilibrium occurs. It's at that point that we can measure the pressure and say, okay, that is the vapor pressure at this temperature. The higher is the vapor pressure, the weaker are the IMFs. So the more readily it evaporates, the weaker are the IMFs. Every liquid has a characteristic vapor pressure as a function of temperature. So here we have data for water. We have temperature data in degrees Celsius, and we have vapor pressure data in torr. Notice as we go from 0 to 100, the pressure goes up. And here's a graph, the one in the middle, of vapor pressure in torr versus temperature. We see as temp goes up, vapor pressure goes up. It's not a linear relationship. The last graph is vapor pressure in atmospheres versus temperature in degrees Celsius. When the vapor pressure equals the atmospheric pressure pushing down on it, and that's the atmospheric pressure is usually 1 atmosphere if we're at sea level, then we have boiling occurring. So notice, go on our graph to vapor pressure 1 atmosphere, go over to the graph, drop down to temperature, you see 100 degrees. That would be the boiling point, what we call the normal boiling point. So these are phase diagrams, and we will cover phase diagrams more in the activity that's coming. As temperature increases, vapor pressure increases. We saw that on the graph. At higher temperatures, a greater percentage of molecules have enough energy to break the IMFs. Thus, more molecules exist in the gas phase at the higher temperature, and the vapor pressure increases. For example, on a hot day, a swimsuit dries a lot more quickly than it would on a cooler day. The normal boiling point is the temperature when the vapor pressure is equal to 1 atmosphere, or we could say 760 torr. And we saw in the diagram, plus we know it already, for water, the normal boiling point is 100 degrees Celsius. All right, so in an example below, we're going to work with an equation that has a logarithm in it. So here's a quick logarithm review. Log, log, is to the base 10. And ln, the natural log, is to the base e, where e is, like 10, a number, but its number is 2.71828, and it goes on from there. So log to the base 10, ln to the base e. The log of 100, that means what is the exponent on 10 that gives you 100? Well, the exponent on 10 is 2 to give 100. That means the log of 100 is 2. And you can get that in your calculator by typing log 100, enter, you get 2. Now, the natural log, if we're given the problem, what's the natural log of 7.39, it means to us, what is the number on E that gets us 7.39? Well, if we type in ln of 7.39 in our calculator, we get the value 2, because e to the 2 is 7.39. Alrighty, so go over that stuff again if you feel like you need to make sure that you remember what logarithms are all about. So in our graph on the left side, where we have water, ethanol, and diethyl ether, we have vapor pressure in torr versus temperature. So we're seeing the vapor pressure graphs for those three different compounds. And we can get from those data, if we had the data, a linear graph if we plotted not P vap versus temperature, but ln of P vap versus 1 over T, where T is now in Kelvin. And that's what we're seeing in the graph B. So ln of P vap versus 1 over T in Kelvin. And then we have linear functions for each of those three different substances. And it turns out that we have not proven it, but the equation that describes that linear relationship, ln of P vap equals negative delta H of vaporization over R, where R is the ideal gas constant, 8.314 joules per mole Kelvin, times 1 over T plus C. That equation, which I've written below there, is called the Clausius-Clapeyron equation. In the last column of that table, we have data for water. So we were given the temperature versus pressure data for water above. If we converted those temperatures to Kelvin and inverse them and took the natural log of the vapor pressures, we would end up with those columns of data. If we plotted that data, fitted it to a linear function, and our plot is ln of P vap on the y-axis, 1 over T on the x-axis, we would end up with a slope from our linear fit of negative 5201. The unit turns out to be Kelvin because ln, anytime we ln or log something, we get rid of units. So the y-axis has no units, it's unitless, but the x-axis does have unit 1 over Kelvin. So when we simplify that, we see the slope has units of Kelvin. Alrighty, so going to our Clausius-Clapeyron equation and equating it with a straight line, we have ln P vap on the y-axis, 1 over T on the x-axis. That means if you just go straight down, the slope m is equal to negative delta H vap over R. The y-intercept b is equal to c in our Clausius-Clapeyron equation. The big thing, the important thing for us is if we know that if we have vapor pressure versus temperature data, we make that ln of P vap versus 1 over T graph, fit it to a linear function, and get a value for the slope, we can determine delta H of vaporization of that liquid from the data. Alrighty, so here's a problem. Consider the graphs above for diethyl ether, ethanol, and water. There's a couple problems I want you to come back to and do on your own. And we will look at the third problem together. Using the Clausius-Clapeyron equation and the slope of the ln P vap versus 1 over T graph, calculate delta H vap for water. Okay, so what we have is that the slope is equal to m equals minus delta H vap over R, or we have delta H vap is equal to minus mR. So we have minus a negative 5201 Kelvin times 8.314 joules per mole Kelvin. Doing the math, we get 43240 joules per mole, or 43.24 kilojoules per mole. In the vapor pressure experiment that is, I believe, our last experiment of this semester, we'll make a calculation very similar to this. So look back over here if you need to remind yourself what that was all about. Here's an example problem for you to look at. So come back and do that one. Changes of state, our next topic. So those would be, for example, going from solid to liquid to gas, or any combination in there, going in forward direction, back direction. Looking at the solid to liquid change, that's an endothermic process. That would be melting. It takes energy to melt something, and this occurs at the melting point, MP. The amount of energy it takes, the delta H, which is greater than 0, is often referred to as delta H of fusion, where fusion basically means melting. If we reverse that, we go from the liquid to the solid. That's freezing. It occurs at the freezing point, where the freezing point and the melting point are the same temperature. Delta H of freezing is going to be less than 0 for this exothermic process. We have to take away energy from the liquid to make it a solid. Delta H of freezing is equal to minus delta H of fusion. If we go from the liquid to the gas phase, that takes energy. That's an endothermic process. That would be vaporization. This occurs at the boiling point, BP. Delta H of vaporization is greater than 0. We just calculated it for water to be that positive 43 kilojoules per mole. To go from the gas to the liquid, so going the other direction, that's exothermic. That would be a condensation process. It would occur at, we could say, the condensation point. It's the boiling point. And the delta H would be less than 0. We can also go from the solid phase directly to the gas phase. That's an endothermic process. That takes energy. That process is referred to as sublimation. A heating curve is a graph of temperature versus heat added. Heat is usually added at a constant rate, so a heating curve could also be temperature versus time. We have two heating curves shown. The middle one is for water. The left one is for a material other than water. And let's go to the water one. And in this one, we have the temperature going from negative 20 degrees up to 140 degrees. So what we're starting with is water as ice, and it takes energy to go from negative 20 degrees upward, and the temperature is increasing as we do that process up until 0 degrees, until it starts to melt. The heat added causing a temperature change, that we could calculate from the equation Q is equal to ms delta T, where the S that we use, we see in that last column, is for solid water having the value of 2.03 joules per gram degrees Celsius. So that would describe the amount of heat that must be added to have it go from the negative 20 to the 0 degrees. Once we get to 0 degrees and we're starting to melt the ice, it takes energy to do that. We're overcoming IMFs, but notice that the temperature doesn't go up any. And that's because all that energy is going into overcoming the IMFs. The equation we would use to describe that amount of heat is equal to delta H of fusion times the moles. You see delta H of fusion given for water to be 6.02 kilojoules per mole. Once it has all melted, we have all liquid, then as we continue to heat it, we're in the green portion of the curve, and we notice as we add heat energy, the temperature goes up. And the amount of heat we would have to add would be given by Q equals ms delta T, where the S would be for liquid water, 4.18 joules per gram degrees Celsius. When we get to 100 degrees, so that now we're starting to vaporize or causing it to become a steam, we have once again a flat portion of our curve. We add heat energy. The amount would be given by delta H of vaporization times the moles involved. The value we use is 40.7 kilojoules per mole. That is the delta H of vaporization. And all of that energy is going into overcoming the IMFs. Notice delta H of vaporization is much larger than delta H of fusion. It takes a lot more energy to completely overcome the IMFs to go from the liquid phase to the gas phase than just to go from the solid to the liquid phase. So once it's all vaporized, then we are in the red portion of our graph, and again the Q is given by Q is ms delta T, where we're using the S to be 2.06 joules per gram degrees Celsius. So the temperature remains constant during a phase change. That occurred when the ice was melting. That occurred when the liquid was vaporizing. All the energy is used to break the IMFs. So we have a couple of examples. Come back and look at those on your own. The example that we'll look at together is calculate the heat required to heat 110 grams or 5.5 moles of solid water at -10 degrees Celsius to gaseous water at 110 degrees Celsius. Don't confuse the 110 grams with the 110 degrees Celsius. Just coincidentally, those are the same numbers. Alrighty, so the total amount of heat energy that would have to be added is given by the heat required to go from the -10 to 0 degrees plus the heat to fuse the solid, to go entirely from solid to liquid, plus the heat to go from 0 degrees to 100 degrees, plus the heat to completely vaporize the liquid, and then plus the heat to go from 100 degrees Celsius to 110 degrees Celsius. So what we have is Q is mss delta Ts plus N delta H fusion plus MSL delta TL plus N delta H VAP plus MSG delta TG. So putting in our numbers, we have 110 grams times 2.03 joules per gram degree Celsius times T final, 0, minus T initial, -10 degrees Celsius, plus 5.5 moles times 6.02 times 10 to the 23rd joules per mole, plus 110 grams times 4.18 joules per gram degree Celsius times T final, 100, minus T initial, 0 degrees Celsius, plus 5.5 moles times 40.7 times 10 to the third joules per mole, plus 110 grams times 2.06 joules per gram degree Celsius times T final, 110, minus T initial, 100 degrees Celsius. Notice that we had to go from the kilojoules of the delta H of fusion and delta H of vaporization to joules for consistency of units. So we would calculate 317,000 joules or 310 kilojoules to 2 sig figs. All right, so there's another problem, couple of examples for you to look at, so come back to those. Now we're getting into the section on solids. Solids can be divided into 2 categories. A crystalline solid has a repeating, that is, crystalline structure. So there would be some kind of a repeating structure in it, like take quartz crystal. And we see that we have, it looks like a bunch of hexagons in the structure. An amorphous solid does not have a crystalline structure, that is to say, does not have a repeating structure. Quartz glass, by contrast, was cooled much quicker than quartz crystal was from the molten stage, and that causes it not to have enough time to make for a repeating structure, so it does not have a repeating structure. Butter, rubber, those kind of solids are these amorphous solids. Some would say technically an amorphous solid is really a very, very viscous liquid. Okay, we will work with crystalline solids, the ones that have the repeating structure. It turns out they come as several different types. So looking at our solid column, we have metallic solids, ionic solids, network solids, molecular solids. The last category, group 8A solids, I put just to be complete because your book has that. We really won't do much with that category. It's not very common. Metallic solids, their particles are a bunch of atoms. The bonds between those atoms is the covalent bond, basically the metallic bond. Melting points of metallic solids are variable. Indeed, they tend to be high, at least for the common metals in our everyday life, the industrial metals, iron and chromium and copper and zinc. Those have high melting points. But technically, sodium is a metal. It has a pretty low melting point. Gallium, that has a low melting point. Mercury is a liquid at room temperature, so that's why we have variable there, but it's more on the high side for the more common metals. Metals, their conductivity is yes, they conduct. They have mobile charges, they conduct. They're not soluble in water. Okay, there's an example of copper, its melting point given as over 1,000 degrees Celsius. Ionic solids, sodium chloride, for example, there we have the particles being a bunch of ions held together by the ionic bond. Melting points of ionic compounds are high. It would be difficult for us to ever try to melt an ionic compound on our typical stove in a typical home. They do not conduct. Although they are made of ions, the ions are not mobile, so they cannot conduct. Some ionic compounds are soluble. In fact, probably most are soluble, but definitely there are a lot of ionic compounds that are not water soluble. So that's why we have yes, no there. Example, sodium chloride with its melting point of a little over 800 degrees Celsius. Network solids, those are ones like diamond, graphite, sand. Those are ones where we have a bunch of atoms that are held together by covalent bonds, and we know covalent bonds are strong, so they're hard to melt. They don't conduct. The particles tend not to have charges, so most network solids do not conduct. They would not dissolve in water. Imagine trying to dissolve, though why would we want to? Diamond. Diamond is an example, and it has a very high melting point, so almost 4,000 degrees Celsius. Molecular solids, those would include ice, sugar, dry ice, solid CO2. What we have in a molecular solid are molecules that are held together by IMFs. We know IMFs in comparison to the ionic and covalent bonds are much weaker. So molecular solids have low melting points. They don't have mobile charges, so no, they are not conductors. They might be soluble in water if they're polar, or not if they're nonpolar. sugar, or we could say that's glucose, C6H12O6. That's an example. Glucose has a melting point of 140 degrees Celsius. Sucrose, that's table sugar, that's also a molecular solid. That last category, there we have atoms held together by only London dispersion forces. Argon solid would be an example of that. Melting point's low because IMFs are low. They're not soluble in water, they don't conduct. They're also not very common. So here are several examples. The first one is is diamond, and that's a network solid. The black balls in that diagram are carbon atoms, and they are covalently bonded together. It's just a bunch of carbon with those tetrahedral structures covalently bonded together. Being covalent, those bonds are hard to break, thus the high melting points. The next example is what sodium chloride looks like. And we have a bunch of ions there that are held together by the strong ionic bond. That's why ionic solids are hard to melt. The last example is a molecular solid, and that is actually ice. So we have a bunch of water molecules held together by those IMFs that are given in this example, this picture by the blue dots. The first category that we will spend time talking about are the metallic solids. Just a little bit on why they conduct. So one description of a metallic solid is called the electron C model, where we have like you could say a chunk of sodium metal or a chunk of magnesium metal. So we have the atom with the valence electron, in the case of sodium, 1 valence electron, in the case of magnesium, 2 valence electrons, that are somewhat loosely bound to the rest of the atom being the nucleus and the core electrons, somewhat loosely bound. In our picture there, for sodium, for magnesium, we have Na with shown plus, that would be the nucleus and the core electrons, with that electron, that valence electron that's kind of loosely bound to it. Magnesium, the core with the nucleus, core electrons, nucleus, 2+ charge because of the 2 electrons, valence electrons loosely bound to it. So under our text there we have core electrons and nuclei, cations, are localized with each atom, and valence electrons are shared over the entire metal. Those valence electrons that are shared throughout are mobile, and that allows metals to be good conductors of heat and electricity. And the cations can easily slide around, making the metal malleable. So we can pound a metal to a shape. That means it's malleable. Okay, so that's a little bit on the conductivity of metal. Now we will spend time looking at structure. We determine the type of crystalline structure a metal has using a technique called X-ray diffraction. And we will make models, we will make theoretical descriptions of metals, which are our models, and for those we will spend time looking mainly at 3 different kinds of models, 3 different lattice structures. Crystalline lattice, so look at those in our diagram, look at the last diagrams. We have the crystalline lattices. We have the simple cubic structure, and for that we are saying atoms are spheres, so those round balls are the atoms. Make a layer of round balls, and then directly above it make another layer just like that, where you put the second layer directly on top of the first layer, third layer directly on top. If so, we end up with a simple cubic structure. We can separate our layers a little bit and insert an atom in between them, kind of in the dimple there. And those atoms, although shown green and white, those are all the same kind of of metal, like all sodium or all magnesium. The different colors are just used to show the different positions of the atoms, but they're all the same type. If a metal crystallizes in that structure, it's called body-centered cubic. If we have a slightly different structure, where there's even more balls in between those layers, and they're at the face positions instead of more in the body in the center, we have face-centered cubic. So we have some metals that crystallize in simple cubic, some in body-centered cubic, some in face-centered cubic. And which one the metal takes on, we find from X-ray diffraction. Now, when we make our models and do our calculations, what we want is to work with what we call a unit cell. That is the repeating structure, the smallest repeating structure. So for simple cubic, if we were to cut it down, we would find that we have that, what we call the simple cubic unit cell, the one shown in the middle of our diagram. If we have body-centered cubic crystalline lattice, then we have for its unit cell what we call the body-centered cubic, the BCC unit cell. We have an atom in the middle, and then we have those 4 or those 8 corner pieces around it. Notice simple cubic is only those 8 corner pieces. And then face-centered cubic, FCC, there we have half of a face atom on each of the 6 sides of the cube, as well as those 8 corner atoms. Some terms that we're going to be seeing are, okay, unit cell, we've talked about that, crystalline lattice, we've talked about coordination number, that is how many nearest neighbors does each atom have. Go to the very middle structure, the body-centered cubic unit cell. Take that ball in the very center, the atom in the center, and it's touching those 8 corner atoms. So that one has a coordination number, Cn, of 8. The simple cubic has a coordination number of 6. The face-centered cubic has a coordination number of 12. And we will see those talked about again, so we can try to understand more why the 6 and the 12, but the 8 I think you can pretty easily see. What we're going to do is, from our model, we're going to calculate the density of a metal, and we're going to compare it with an experimental density, and the closer those two are to each other, the more we can be happy that we're describing it correctly. Density, remember, is mass over volume. For the mass part, what we're going to do is determine the mass in a unit cell, so mass per cell, and then for the volume part, we're going to determine the volume per cell. So ultimately, we will calculate density equals to mass per cell over volume per cell. Notice the per cell part cancels out. We'll calculate the density, that it turns out the area density, in 2 dimensions, 2D first. It's a little easier to visualize, and then we'll go into 3 dimensions, 3D. So in 2 dimensions, we're working with circles, not spheres, not atoms, so just circles, like imagine pennies. It turns out that there are 2 ways of packing circles, giving 2 lattices. We can have lattice 1, so we make a row of circles, second row, third row, and we just put the rows on top of each other. We're not packing them tightly. This is what we're going to call lattice 1. It's also not the closest packing, not CP. Because we have a closest packing arrangement, a lattice, that's lattice 2, where we have that same first row of pennies, we take the second row of pennies and we position it over the first such that it kind of falls into the first. It goes into the dimples of the first. We do that also with the third layer So we get more packing of the pennies. We're calling lattice 2 the closest packing one, lattice 1 not closest packing. Now we have to look at the unit cells for these two lattices. So for lattice 1, it would just be that square shown. That is to say, that repeats over and over to make up that lattice, that overall lattice. For lattice 2, there's several kinds of unit cells, as shown in that picture. The rectangular one, the one with 90-degree angles, turns out to be the easiest one to work with, so that's the one that we will work with. All right, so we're going to calculate the area density for the pennies from lattice 1 and from lattice 2. And we have to have, to compare it with, well, actually, I don't have a comparison area density, but we do have comparison densities for metals. So we will make that comparison with metals between our model and the actual experimental data. Anyway, for the penny, we have mass per penny. I weighed a penny and got 2.5 grams and measured the radius and got 0.90 centimeters. So we're going to use those numbers in our calculations. Okay, so density is, in our area density, will be the mass per area. The mass is the mass per cell. The area is the area per cell. And we have then density is mass per cell divided by area per cell. Okay, so mass per cell. So for the mass per cell, what we have to do is figure out how many pennies we have in a cell and multiply that then by the mass per penny. Okay, so number of pennies in the cell. For lattice 1, and we see our unit cell there shown shaded, we have number of pennies per cell. Well, we have four quarters of a penny, so we have the equivalence in one unit cell of 1 penny. So we would say there's 1 penny per cell. For lattice 2, we have those 4 quarters, but we also have a penny in the middle. So we end up with a total of 2 pennies per cell. Okay, next we do the mass per cell. So we're doing our whole equation. Now that we know the pennies per cell, we're multiplying then each of those quantities by the mass per penny. So for lattice 1, mass per cell is 1 penny per cell times 2.5 grams per penny, equaling 2.5 grams per cell. For lattice 2, mass per cell is 2 pennies per cell times 2.5 grams per penny. We get 5.0 grams per cell. All right, so we have the upper part of our area density equation. Now we need the lower part, the area per cell part. Okay, so area per cell, we're doing that for lattice 1 first. We're going to call our length of our unit cell L, as we see in the diagram. So area per cell is going to be length squared. Well, the length is 2r, so area per cell is the quantity 2r squared. Area per cell, then we have 2 times 0.90 centimeters squared. Remember, the radius of the penny was 0.90 centimeters. So we get for lattice 1 the area per cell to be 3.24 centimeters squared. For lattice 2, for the area per cell, well, we see in our diagram there for our unit cell, we have one of our lengths, the horizontal one, to be 2r. The vertical length is, we can't immediately say what it is in terms of r, but we do have that the hypotenuse is 4 radii, or 4r. And using Pythagorean theorem, because we have 90-degree angles here, we can determine what the length is in terms of the radius, because the radius is what we've got a number for, 0.90 centimeters. Okay, so applying Pythagorean theorem, we have 4r squared, hypotenuse squared, equals 2, the length squared plus the 2r quantity squared. So we have 4r squared is equal to 2r squared plus l squared. Solving for L squared, we have L squared is equal to 16R squared minus 4R squared, or L squared equals 12R squared. L equals the square root of 12 times R. Okay, so applying all that to our lattice 2, area per cell is 2R times L. Area per cell is 2R times the square root of 12R. Area per cell is 2 square root 12 R squared. So the area per cell is 2 square root of 12 times 0.90 centimeters squared. The area per cell is 6.93 centimeters squared. Alrighty, so now we have the area per cell for both lattice structure. So now we can calculate the density, putting all of our stuff together. So density is mass per cell over area per cell. So for lattice 1, we got the mass per cell to be 2.5 grams per cell. We got the area per cell to be 3.24 centimeters squared per cell. And we end up with an area density of 0.77 grams per centimeter squared for lattice 1. For lattice 2, we have the 5.0 grams per cell from above divided by 6.93 centimeters squared per cell. And we get 0.89 grams per centimeter squared, a bigger area density than for lattice 1 because it's the pennies are more tightly packed in that arrangement. When we compare the space occupied by the pennies to the space that could be occupied, this is called the packing efficiency, we get these results. So we have not proven this. Actually, in the activity that you will do on crystalline solids, you will see that calculation. Anyway, if you compare the area that could be occupied to what is occupied, then you end up with lattice 1, 78% of the space that could be occupied is occupied, whereas in lattice 2, the closest packing, the way to get the most pennies together, 90.7% of this space is occupied. Since the closest packing structure maximizes the packing of pennies, it follows that that is lattice 2, would have the greatest area density, 0.89 grams per centimeter squared, and the greatest packing efficiency, 90.7%. Okay, so also that coordination number, the number of nearest neighbors. So in lattice 1, take any penny, take a middle one, and you would count it's touching 4 neighbors, so it has a coordination number of 4. In lattice 2, take that middle penny and you count it's got 6 nearest neighbors, so it would have a coordination number of 6, and that's where those two values come from for coordination number. All right, so a summary. For the lattice 1, pennies per cell, we have 1. For lattice 2, we have 2. The area per cell, that equation comes out to be 4r squared, whereas for lattice 2, it comes out to be 2 square root 12 times r squared. Coordination numbers, we see 4 and 6. So these results, including the area density and packing efficiency, but of course would have to put the correct mass per circle and radius into the area density calculation, they would apply to any two-dimensional circular object packed into these lattices. So they would apply to coins, discs. It doesn't matter how big they are, it would apply. Of course, each one would have its own area density depending on the radius and the mass of that circle. So important parts are the unit cell, the type of unit cell, closest packing, not closest packing, the number of items per cell, pennies per cell in the case of spheres and pennies, the area per cell, and the coordination number, because we're going to see those quantities are important to us as we move now into 3 dimensions. Okay, so here we go with 3 dimensions. So 3 dimensions, as we talked about before, we use X-ray diffraction to find the structure of the metal and the radius of the metal atom. So we get that information from experiment, and we apply our modeling using those numbers. Closest packing is one kind of structure found in metals. There's many kinds of structures. So closest packing is one. That's where the atoms are as close together as possible. There are 2 types of closest packing structures. We have the hexagonal closest packing, which makes for a HCP, hexagonal closest packing cell, and we have the cubic closest packing, which makes for the unit cell we call the face-centered cubic cell, or the FCC cell. They both have the greatest packing efficiency of all the different kinds of ways metal atoms pack, where the packing efficiency is the space occupied over the space available. Of all 3-dimensional structures of spheres, and in this case 74% of the space is occupied by spheres. So in both hexagonal closest packing and FCC closest packing, 74% of the empty space is occupied by spheres or by atoms. Alrighty, now these diagrams are a little bit hard to see perhaps here, but in the activity on the closest crystalline solids, you'll be working more with these and it'll make it a little bit clearer. But here's the best that I could do. So closest packing, we have that shown as the 2 different situations. The hexagonal closest packing, that's the upper row, and then the cubic closest packing, the FCC, that's the lower row. And we're in the first column. The closest packing structure of spheres. So those are the 2 possibilities. In each layer, and the layers are given by the yellow ball, the balls, the blue balls, the green balls. In each layer, a given sphere is surrounded by 6 others, creating 6 dimples. So the dimples are the little divots where the balls are touching each other. Only 3 can be occupied by the next layer. So imagine we have 6 atoms surrounding an atom, and there are 6 dimples in there. Well, if we put another layer just like that on top, it turns out only 3 of those 6 dimples can be occupied just because of the volume of the atoms. In the upper row, that's the hexagonal closest packing, the HCP one, also referred to here as the ABAB packing. The second layer is like the first layer, so the second layer being the blue layer. So the second layer is like the first layer but displaced so that each sphere in the second layer occupies the dimple in the first layer. The spheres in the third layer, so that would be the yellow layer, the spheres in the third layer occupy the dimples in the second layer so that the spheres in the third layer lie directly above those in the first layer. And that's how we get that ABA layering. Okay, so we're talking the upper row A, Go to the third picture. We have the first layer, yellow, layer A. We have the second layer, B, blue. Then we have the third layer directly on top of the first layer. So again, we're calling that layer A, and then we have layer B. So that's what hexagonal closest packing is. Layer A, layer B, another layer A, layer B. In the row B, the second row there, we have the face-centered cubic, the ABC packing. In the ABC packing, FCC, the spheres in the third layer occupy the dimples in the second layer so that no sphere in the third layer lie above any in the first layer. So go to the last picture there. We have layer A, yellow, layer B, blue. Then we have layer C, green, because layer C is not directly on top of layer A. After that, however, we repeat. So we have ABC, ABC, and so on. In the middle column of our table, we have the hexagonal closest packing shown again. So we have layer A, layer B, layer A. It goes back and forth like that. The unit cell is shown in the upper row there. It turns out its angles are not 90 degrees and it's not a cube. So in the AB packing, the unit cell is hexagonal, that is HCP. The length, width, and height are not equal to each other. It's not a cube, and all angles are not 90 degrees. We will not make calculations with this structure, but what is shown in the diagram has to do with coordination number. So the ball there in the middle of layer A, shown in red, it is surrounded by, in that layer, 6 balls. In the layer above it, 3 balls touch it, given by those balls 7, 8, and 9. And then in the layer below it, 3 more balls touch it. Those are given by 11, 12, 10, 11, and 12. So that ball in the middle is touching 6 plus 3 plus 3, or 12 other balls. The coordination number is 12 for hexagonal closest packing. It turns out for face-centered cubic, the other closest packing, its coordination number is also 12. Okay, our third column there is the FCC, the ABC packing, FCC unit cell. In the ABC packing, the unit cell is the face-centered cubic cell, FCC. Being a cube, the length, width, and height are equal to each other, and the angles are 90 degrees. In our picture there, we see the unit cell. We will make calculations with this structure. Some metals do not have a closest packing structure. We will work with 2 not closest packing structures. Those 2 are their unit cells, the simple cubic cell, SC, and the body-centered cubic cell. We saw those earlier. Okay, so the 3 cubic unit cells that we will work with, that is the ones where the unit cell is a cube, not necessarily closest packing, but a cube, are the simple cubic. We see what its unit cell looks like. We see an extended version of it in the lattice structure. We'll be working with body-centered cubic, and that has the ball, if we look at the unit cell, in the middle. And then we will work with face-centered cubic, FCC. This is the one that is the closest packing. So there we have face balls. We don't have a body ball. We don't have a ball in the very middle, but we have balls on the faces. Plus, all 3 of these have the corner pieces, corner balls, corner atoms, corner spheres. Okay, we will need to determine the net number of atoms per cell. We'll have to do that for simple cubic, body-centered cubic, and face-centered. So here's an example of showing how we make that calculation. In order to determine the net number of atoms per cell for the FCC structure, consider the diagram to the right. The one below is just a reminder of what the FCC unit cell looks like. So we have the diagram with A, with B, with C. In A, we're looking at corner atoms. So we've got that red box, which is representing the unit cell, and we see that it's showing one corner atom. The atom at the corner of the red cell is shared with 7 other cells. It is in a total of 8 cells, its own plus 7 others. Thus, 1/8 of it lies within the red cell. Since there are 8 corner atoms in a cube, there are 8 of these 1/8 pieces. Or we could say 8 times an 8, 8 times 1/8 equals 1 net atom for these corner atoms. The FCC unit cell also contains face atoms, and that's shown in diagram B. The atom on the face of the red cell is shared with 2 cells, itself and the neighbor. It is in a total of 2 cells. Since there are 6 faces in a cube, there are 6 of these half pieces. 6 times a half equaling 3 net face atoms. Thus, for FCC, there are 8 times an 8th plus 6 times a half, or 4 atoms per cell. And that's always true in the FCC structure, regardless of which metal we're talking about. All right, so here is the 3 cubic cells that we will make calculations with, and we see simple cubic, FCC, and body-centered cubic. Our next column is atoms per cell. So simple cubic has only corner atoms. So we have 8 times an 8th. For simple cubic, we always have 1 atom per cell. For face-centered, we calculated the 4 atoms per cell above. Body-centered has corner atoms and an atom in the center of the cell. So it has 8 times an 8th plus 1, or 2 atoms per cell. Our next column is the length of the cell, L. So we see in our diagram for simple cubic that length is equal to 2r. So if we knew the radius of the metal we're working with that crystallizes in this simple cubic structure, we would multiply the radius times 2, and we would have the length of the unit cell. For face-centered, so that involves a little bit more calculating. So in our diagram, we see that the atoms on the hypotenuse are the ones touching. So the hypotenuse is 4r, and then we're calling each of the lengths L. So using the Pythagorean theorem like we did earlier, we have hypotenuse squared equals length squared plus length squared. We have 4r squared equals L squared plus L squared. Solving for L, we end up with, on our next line, 2L squared equals 16r squared. L squared equals 8r squared. L is equal to the square root of 8r, which comes out to be L equals 2.828r. For the body-centered, it would be a similar but a little bit more involved kind of Pythagorean theorem calculation. If we went through that, we would find that the length is equal to 2.309r. Okay, our next column is volume per cell, which we need, of course, for our density calculation. So these are cubes, so the volume per cell is the length of the cell cubed. We have the lengths already calculated. So for simple cubic, volume per cell is 2R cubed. For FCC, volume per cell is 2.828 R cubed. And for body-centered cubic, the volume per cell is 2.309 R cubed. Okay, coordination number. Alrighty, so for simple cubic, focus on the upper center atom, the one that's most center in that picture of the unit cell, the upper center atom. It touches 3 atoms that we can see. It also touches 3 other atoms that we don't see. You just have to imagine them. There's an atom above, there's an atom in the front to the left, and there's an atom to the front, in the front to the right. For simple cubic, the coordination number turns out to be 6. Perhaps looking at another picture, a more expanded lattice structure of simple cubic would help you see that. Also, I think that you will see that when you do that crystal lattice, crystalline solid activity. Okay, for face-centered cubic, choose the top face atom. It touches 4 atoms beside it. We can see those. And 4 atoms below that. We can, using our imagination a bit and the picture, we can see that. It also touches 4 atoms above it that we don't see. The coordination number is 12. So for body-centered cubic, choose the body atom, and it touches 8 atoms that we can see. Coordination number is 8. Okay, so a summary. So we have packing types. We have cubic or closest packing. And for those, we have 2 possible situations for the cells. We have hexagonal closest packing, and we have face-centered closest packing. So that's FCC. The efficiency, I told you earlier, though we haven't proven it, is 74%. The atoms per cell for HCP, we're skipping. We're not really making calculations with HCP. The atoms per cell for FCC we found to be 4 from earlier. For the not closest packing, those come as 2 types that we will work with: body-centered cubic, BCC, and simple cubic. Though we haven't proven it, the efficiency, packing efficiency of BCC is 68%, and that of simple cubic is 52%. Notice that for the tightest packing, the closest packing, we have the highest efficiency, 74%, and then for the others, we have lower packing efficiencies. Atoms per cell, for the first, we skip. For the FCC, we have, we already went over those, 4, 2, and 1. Okay, the length, first one we skip. The length for FCC we found above is 2.828 R. For BCC, 2.309 R. And for simple cubic, 2 R. The volume per cell, so for FCC we have 2.828 R quantity cubed, BCC 2.309 R quantity cubed, and for simple cubic 2R cubed. So the coordination number for the top 2 is 12, then we have 8 and 6. And then here I'm just giving you some metals that crystallize in those structures. So again, we analyze the metal with X-ray diffraction and we determine what kind of packing it takes on. And from that we can also determine the radius, and then we can work with determining the theoretical densities and we compare them to the experimental densities. So here's a problem that I think you can do. Calculate the length of 1 unit cell of crystalline gold. Gold adopts the FCC arrangement. The radius of the gold atom is 135 picometers, and we're told that 1 picometer is 1 times 10 to the minus 12 meter. So you actually don't need that conversion, but just so that you would know what it is, because you will need that conversion in the future. So you can calculate from the radius the length of 1 unit cell, since you know the radius and you know that its unit cell is FCC. So this table, the summary table above, I think you will find useful as you do homework problems, quiz problems, and probably that crystalline solids activity. Okay, so when we calculate the mass per cell, so remember, for density we need mass per cell and volume per cell. Volume per cell, we've got that in the table above. For the mass per cell, we have to know the number of atoms per cell, which we know for simple cubic, for FCC, and BCC. They're in our summary table above, the atoms per cell. So we take the atoms per cell, and then we divide by Avogadro's number, because we see with the way it's set up, atoms cancel out, and now we have moles per cell, and then we look up the molar mass of that metal and we multiply by that, because then we see moles cancel out and we end up with grams per cell. So that's how we end up getting the mass per cell. Atoms per cell divided by Avogadro's number times molar mass. Okay, so here's an example. Calculate the density of crystalline polonium in units of grams per cubic centimeter, because that's what we get from experiment. Polonium adopts a simple cubic arrangement. The radius of a polonium atom is 167 picometers, where we see the conversion. All right, so density, mass per cell over volume per cell. So first we will calculate the mass per cell. As we talked about above, it's the atoms per cell divided by Avogadro's number multiplied by the molar mass. So simple cubic means we are multiplying by 1 atom per cell. Oops, I have 4 atoms per cell shown. It should be 1 atom per cell. And then we divide by Avogadro's number, and then we multiply by the molar mass of polonium, 209 grams per mole. So that is equal to, I'm not sure if I have the 1 atom per cell or 4 atoms per cell. Let me do that quickly. Yes. Okay, so I have the correct number for the mass per cell, but I have the wrong value for atoms per cell. So in your notes, change that 4 atoms per cell to 1 atom per cell, and you would get 3.47 times 10 to the minus 22 grams per cell. Alrighty, so that gives us the mass per cell. And next, we're converting from the picometers to centimeters. Okay, so we take the 167 picometer radius, we multiply by 1 times 10 to the minus 12 meters per picometer, and then we convert from meters to centimeters. 100 centimeters equal 1 meter. So we get 1.67 times 10 to the minus 8 centimeters for the radius. Alrighty, so now we're ready to get the volume per cell. Volume per cell for simple cubic is 2r cubed. So we put in 2 times 1.67 times 10 to the minus 8 centimeters cubed, and we get then the volume per cell to be 3.73 times 10 to the minus 23 cubic centimeters per cell. Alrighty, now we've got the mass per cell, we have got the volume per cell. So we take our 3.47 times 10 to the minus 22 grams per cell, and we divide by 3.73 times 10 to the minus 23 cubic centimeters per cell, and we get 9.31 grams per cubic centimeter. Experimental value is 9.32 grams per cubic centimeter. And that's wonderful because then we have that close agreement between experiment and theory, and so we can feel confident with our theory, with our approach, with our model. Our next problem is a metallic solid forms an FCC unit cell with an edge length, that would be L, of 392 picometers and a density of 21.45 grams per cubic centimeter. Calculate the molar mass and the radius of this solid. Okay, so first off, we're taking the length in picometer and converting it to centimeter. So run through that yourself. We would get 3.92 times 10 to the minus 8 centimeters. Now, in order to get the molar mass, we have to get the mass per cell. We have the length, so we can calculate the volume per cell. We also have the density. So we can take the density, multiply by the volume, and we end up with mass, or mass per cell. So that's our plan. Okay, so volume is L cubed. So we have 3.92 times 10 to the minus 8 centimeters cubed, equaling 6.024 times 10 to the minus 23 centimeters cubed per cell. Now we're going to take that volume and multiply by the density. So we do 6.024 times 10 to the minus 23 centimeters cubed per cell times 21.45 grams per cubic centimeter. So cubic centimeter cancels out. We get 1.292 times 10 to the minus 21 grams per cell. Now, by dimensional analysis, we are going to go from grams per cell to grams per mole, or molar mass. So we take the grams per cell. Next, we convert from the grams per cell to grams per atom, and then we finally use Avogadro's number. So just set it up so units work out in this dimensional analysis. Okay, so we take our 1.292 times 10 to the minus 21 grams per cell, and we multiply by one cell is 4 atoms, because that's what we have with FCC, and that's what we're told is our unit cell for this problem. Cell cancels out, and then we multiply by Avogadro's number, because then atoms cancels out. So times 6.022 times 10 to the 23rd atoms per mole, and we get the value 195 grams per mole. Turns out that that matches pretty well with platinum. Okay, so we were also told to determine the radius. So for FCC, the length of the cell is 2.828 times r. Solving for r, we have L over 2.828. So we have 392 picometers over 2.828. We get r to be 139 picometers. Alrighty, so we went over 2 problems. Of course, we went over them quickly. So go back and make sure that you can do those comfortably on your own. Again, we'll talk about ionic solids and network solids and molecular solids briefly. Ionic solids, the structure of most binary, that means made of a cation and an anion, of just simple cation and anion. The structure of most binary ionic solids like NaCl is closest packing. The larger ion, usually the anion, the larger ions are packed into the either HCP or FCC structure, and the smaller ions, the cations, fit into holes among the anions. In sodium chloride, it turns out that both Cl minus ions and Na plus ions have the FCC structure. Okay, so the green balls are the chloride ions because they are bigger than the sodium ones, so they occupy the FCC structure. So hopefully by now you recognize that. Well, there's little vacancies in that structure given by the X's, or you could say the gray balls, and that's where the sodium ion fits in. And that last diagram there is showing the unit structure. In NaCl, Cl minus ions are represented by the green spheres, and Na plus ions are represented by the gray spheres, or the gray X's. In the actual structure, the chloride ions do not touch each other, even though it kind of looks like that. The unit cell shown, okay, is the one on the right. Due to the strong ionic bonds between ions, ionic solids have high melting points. Network atomic solids, or we could just say network solids. This is a model of quartz, which has the empirical formula SiO2. So for every one silicon, there's 2 oxygens. It contains chains of SiO4, except that the oxygen atoms are shared with silicon such that the empirical formula is SiO2. The bonds are covalent bonds, so all the bonds between the O's and the SI's, all of those are the strong covalent bonds. That's what makes this a network solid. So it's a bunch of atoms connected to each other through covalent bonds. The covalent bonds are strong, and this accounts for the high melting point of quartz. Network solids have high melting points. Molecular solids. So this is a model of ice. The red lines represent hydrogen bonds. Since these bonds are relatively easily broken, ice has a low melting point. Molecular solids have low melting point. Remember, molecular solids are composed of molecules. When we melt a molecular solid, like ice, we still have the original molecules. They're just now not in the solid phase, they're in the liquid phase. So all we have to do to melt a molecular solid is overcome the relatively weak IMFs, and that's why they have low melting points. So here's a problem for you to do. Another problem for you to do, a couple more. Phase diagrams, we talked about them just a little bit, and you will spend more time talking about them in an activity. Alrighty, so that's it on our video lecture notes. So lots of problems for you to look at, so definitely go over these lecture notes again by reading through them, by going through the video. Make sure you work on all the problems and feel comfortable with them. Read over chapter 10 in your textbook. It's a long one. Do the assigned homework problems. When the quiz is open, make sure you get in there and take it.